Okay, good evening. So my name is Yvon. I'm the director of LIMSI, and I'm also a CNRS researcher at LIMSI, where I do mostly machine translation. My ambition with this talk is to highlight some recent changes in the field, and also to explain what has changed and what has not, and where also the difficulties remain. So everybody knows that human translation is difficult. Human translation is costly. It's performed mostly by experts that are trained for a long time. And it's so expensive that it is not applicable to any kind of content. I mean, content has to be valuable to deserve a human translation. And this has been known for a long time. And for a long time, people have tried to have cheaper ways to perform translation. And so we know that machine translation has been a goal of AI for at least 70 years now. For the last 20 years at least, machine translation has been based on corpora. So this means that machine translation systems are mostly trained using examples of past translations. And you can find such examples, for instance, in the archives of the European Parliament. And if you have this corpora, and if you have big machines, then you can train machine translation systems. In the recent years, machine translation has turned neural. And this has happened very quickly. Maybe in the course of 1 year, last year, all the top players have switched their systems from probabilistic systems to neural systems. So what has happened, really? You all know this architecture, you all know this graph. So the first machine translation systems were based on the simple architecture, the encoder-decoder approach. And basically what you did is you encode your source sentence. So this is German on the bottom of this slide. So you encode it with a recurrent network, and then you decode the target language. So this is English at the top, one word at a time. And this approach did not work well. It did not work well mostly because when you do that, you encode all the knowledge of the source sentence in the last recurrent state of the source. And this is not enough to remember everything you need to remember in the source sentence to properly decode the target. So the crucial improvement was to add attention to this architecture. So what is attention? Basically, attention is just the ability to use at each time step, the right part of the source sentence to predict the next word. So instead of having one fixed sentence representation, you have as many representations as you want, and you can compute this representation as a weighted sum of the source words. So each time you decode, you look in the source sentence which words are important for the next prediction. And this helped a lot. This helps so much that people today claim that you don't need anything but attention. So just as an illustration, I show you a complex architecture. I won't go into the details of this. This is a paper by Vasvani and colleagues last year. And this paper was called Attention is All You Need. So you don't need recurrent network any longer, as long as you have attention. And in this architecture, you have three kinds of attention. You have monolingual attention between the source words, between the target words, and also cross-lingual attention, so that when you predict a target word, you can look at anywhere you want in the source. And this is not only very efficient, so this is probably the most efficient architecture today. This is also computationally efficient, because as you don't need anymore the recurrent cells, you can compute everything in parallel. So this is fast as well. So this was a huge improvement. So there are other architectures like that. I want to stress, or I don't want to make a point that this is the best system. We will see more architectures, and we will see more changes in the future. The point is, this architecture shows that we need to have good translation systems. We have to mix in the same model a knowledge of the source and the knowledge of the sentence, because translation phenomena in a sentence need to look at both aspects. So we've improved. How much have we improved? So you can find graphs like this. So I'm going to explain. So the x-axis is the time. And as is custom in neural networks, the time starts in 2014, so there is nothing before that. And on the y-axis, you have the translation score. So this is called a bleu. And you can see the improvements. So the first dot, PBMT, was the old system. On the left, you have on the right side, sorry, you have the new systems, and you can see that the improvements for French English, so this is an easy language pair, at least for people in this room. For this translation pair, you can see improvements of about 6 to 8 blood points in 4 years. And this is remarkable. I mean, we were not able to have these large improvements in the past. Let's now look at another language pair, which is more difficult, more challenging maybe, translating from English into German. And here you see, again, the same kind of pattern where we have a great improvement. And in that case, the improvement is even better. It's almost 10 blood points. And I'm not going to stress too much numerical values, but the improvement here is from something that was not useful into something that is useful. So basically, when the blue score is 20, you can't use the translation. When it's 30, you can do something with it. So that was the huge difference. And of course, I won't comment the fact that on these slides, the authors, I'm not the author of this graph, have drawn a line of 50 as being the human quality, which I don't think is true, but we can discuss that later. I'm going to look at some cases where we have made really improvements in translation. The first thing you can notice if you use a translation systems is that the fluency, that is the grammaticality of the target, has improved a lot. So if you read these examples, you will see that. Something else that is that was maybe more difficult to pinpoint is the fact that we are now able to handle what we call in linguistics long-distance dependencies. So, I mean, if you look at these slides, I mean, it's the same sentence in the English, except for one character, the first one. So I turned a he into a she. So I changed her. I just added an s. And in the French, you can see that it not only changed the beginnings from il to elle, but it also changed the agreement of satisfait, pleased, okay, some 20 words away from the change. So this is long-distance dependency, and we are doing this much better than we used to. Another area where we made very good improvements is the robustness against unknown words. So here I have an example of a very complex technical text where you see rare words like bronchodilatateur or corticosteroid that you don't see in everyday's readings, except if you're a physicist. And these were really difficult to translate because how can you translate a word you've never seen, right? I mean, in the probabilistic words, these words were really difficult to translate. But thanks to the plasticity, I would say, of neural representations, now we're in a position to translate these cases using subwords representation. So there have been several approaches to decompose a word into subword units, and we can very easily mix this subword representation with a full word representation and find the translation of these unknown words. A last area where we have made tremendous progress is the robustness against noisy inputs. So I've taken these two examples. These are real cases. You can see a lot of typos and mistakes in the French. So like accueil is misspelled and we miss S at base de données, etc. But I mean, for the system, it makes no difference. It doesn't harm the output at all. So I mean, the output is almost perfect. I mean, it has corrected, as it were, the input before translating. And this is very easy to achieve. It's just a matter of training the systems with noisy inputs. And it's easy to get noisy inputs. So that's really easy to achieve. The last point I wanted to mention is that not only have we made progress in our current systems, but I mean, neural nets have really opened new doors for new applications. So this is an application of the new technology where we try to translate the caption of an image using the image itself as a disambiguation for some words. So here the image on the left can help disambiguate passing, for instance, which is ambiguous in English. So we can go from image to text, or from speech to text, or from several languages at the same time to text, etc. So I mean, a lot of new applications are now possible with these new architectures. I mean, to finish, I would like to also highlight some difficulties that remain, because not everything is solved. I mean, the blue scores is still, depending on the language pair, in the 30s or maybe in the 40s in the best cases, and it's far from a human level. So one first difficulty I'm going to mention is domain adaptation. So domain adaptation is well known in machine learning, and this is a problem you get when you train with data from one type and then test it with data from another type. And we do that all the time in machine translation. Why? Because we don't have enough data for all our problems. We don't have enough data to translate tweets. We don't have enough data to translate speech. We don't have enough data to translate technical documents. So what do? We use the data from the European Parliament, and then we get into trouble. Because if you use the data from the European Parliament, this is not a chair, okay? This is a chair, okay? This is the president of the European Parliament, and this is the chair of most debates. So if you use this data, you will mistranslate chair as president in many, many cases, and you don't know why. It's only because you're using the wrong kind of data. So for this problem, this is a long-known problem. We have recipes, but we don't have theories, and we lack theories. And because we haven't looked, I would say, enough at variation in language, and variation in language is really important. Another problem we have is everything that's related to the extra-sentential or discourse level issues. Look at this. So the English starts as "it's John car," so it translated in French as "c'est la voiture de John." Okay? And from then on, in the French, every pronoun should be feminine because it's la voiture. Okay? But as translation proceeds one sentence at a time, I mean, you look in the translation, all the pronouns are masculine. Okay, and that's wrong. So he says, "c'est la voiture de John." Non, pas du tout, c'est le mien. Okay, this is wrong. It should say la mienne, etc., etc. So everything that goes above the level of one sentence is missed. It's just because in our current architecture, we don't process text, but we process isolated sentence. And in many cases, this is wrong. And this causes problems for reference issues like this, in the argumentation, in the rhetorical structure, and also with this architecture, it's difficult to maintain the lexical or the stylistic consistency, meaning that if you choose a word at the beginning of a text for your translation, you should use this translation consistently and not change at every sentence for a different translation. The last problem is and maybe this is the most serious one, is that in the world of machine translation, we often believe that all we need is a corpus. And this is not true. For many, many translations, we need to have external knowledge. We need to have knowledge of the world. We need to have knowledge of the pragmatic situation. And I've illustrated this with a very nice example by Douglas Hofstadter. So, I mean, you can read it for yourself. So, I mean, in the English, the author is using his and her to make a point that in the house, each of we assume the couple, the man and woman, has his own stuff. Okay, and that's important for them. But when you look at the French, I mean, it's perfect in a way, because, I mean, how would you translate this? I mean, her car is sa voiture, and his car is sa voiture, but the translation misses completely the point. Right? It misses the point because what is expressed here is not about words. It's about a pragmatic situation, and our current systems cannot handle these cases at all. So I'm going to wrap up and by asking a question. I mean, as I have tried to explain, machine translation has improved a lot, has improved for many language pairs, from a situation where it was not useful to a situation where it's useful. And this makes a huge difference because it creates a virtuous circle. We have more users, we have more fundings, we have more data, and this also fosters research to have better algorithms, better architectures, etc. So in a way, this is really good. But have we progressed in translation? Many would argue that we haven't. For the reasons that I've tried to explain, we haven't made any progress for small domains. We haven't made any progress in terms of translating the rhetorical structure. And to conclude, I would say that, I mean, some say translation has improved, and some say translation has not. And this is just because translation has several meanings, and we should have done that from the beginning as computational linguists. Thank you.